Let me just say that again. Hello, everybody, in case that got missed. John says hey. Chris says hey. Mike says howdy. All right. Yeah, we got a couple things to talk about and show today from the realm of FPGA-dom and 6502-dom. The one thing I wanted to start off with is thanks to the contribution of Frank Buss, who sent me some code, and I burned into my one-time programmable EPROM. That's how much confidence I had in Frank. I only had a tube of these things. And sure enough, the code that he sent is running the vacuum fluorescent display you see, and it worked perfectly once I troubleshot some differences with my circuit board. Go ahead. Right. That's true. That's right. It's not silicon. Yeah, right. It's not the silicon nitride. Right, you make an EPROM. Right. I believe so. I believe the gate is a floating gate structure. It's either a four transistor or 6 transistor design. When you increase the voltage VPP to the programming voltage, which is like 24 volts, some high number like that, it'll actually tunnel the charge. Oh, wait, I'm thinking of electrically erasable. But the ultraviolet light does the same thing. It gets access to that floating charge, to that floating gate, overrides it with UV light, and can discharge it. Wow. Hang on. No audio from Ben. I don't even know how to fix that. No, I don't. Say something now.
Something now.
All right, so yeah, people are telling me Ben's on mute. So right now you should be echoing and you're not. So I turned on a backup channel for you. So we're waiting to see if people tell us that. So people, can you hear Ben now? Ben, say something.
I'm not. Actually, on YouTube, I'm not hearing either of us come through on YouTube, but that's probably because I've got the wrong speaker selected in the system.
Okay,
actually.
they're saying that they could hear you now. All right, so okay. Right now, let me be real clear. Right now, you should be echoing your ass off, and somehow now we're not getting an audio channel out of Skype into me. So I went to a backup channel, and that seemed to have worked. So, yay, software. Yeah. So let's start again then, my friend. We started out. You asked about an EPROM. And decapping so to back up even further, we started talking about one-time programmable EPROMs, and you asked about decapping the EPROM.
Yeah, I want to build to bust the myth. If you could actually carefully decap a plastic OTP EPROM and still erase it, because I've heard of people attempting to do that back in the 90s, and I was just curious if that. I
believe that would work, right. Now, that reminds me of a story about my... You knew it would, right?
For.
So, my first week at Commodore, and remember, we're above a chip fab, right? So we've got MOS below us. We've got wizards walking the hallways, right? And so I go into where they're probing a chip. This was the TED chip that later became known as the Plus 4 series, 264 series. And they've got it under a microscope, and they've got these cat's whisker-like probes on a staging device. It's very stable, and they just slide these little platforms around, and they would push it into the silicon, and they called it the rape and pillage mode, where they would shovel the layer aside so to make contact with things. Yeah. So they've got these probes on there, but they can't write to a one of the registers because there's actually a short in the chip. This is the days before we had design rule checks that told electrical rule checks that told us if it matched the schematic. So the fact that A6, 7, and 8 were shorted together, it said that's fine. It's a great short. If it was almost a short, it would bitch. The DRC would bitch. But it was the electrical rule said, nope, nice clean short, whatever you were trying to do, go ahead and do it. So they couldn't put it in NTSC mode to test it. So they've got it under the microscope, and they turn on the microscope light. And they watch the scopes, and they go, we're in NTSC mode, turn off the light. And I'm standing there, and I'm watching, and my jaw's hanging open, and I'm like, did you just use the light from the microscope to flood the gate of the register and cause it to flip? And they go, yeah, yep. And I'm like, I'm working where this is the best place to work. I'm there. I am there. I was I loved it before that day, but after that day, I knew I was working in the right place. So I've seen light being used to flip a dynamic register in silicon.
That's crazy. I've never even thought about that, but it makes perfect sense. We use light to erase things, you know.
Right. Somebody said, I love this story. So people know that story about me already. It is in the book, by the way.
Hey, look, at the end of the day, light, RF, microwaves, or it's all just electromagnetics at the end of the day.
Yep. It's charges, carriers. Yes. Yep. And Chris just said every transistor is a phototransistor. True enough.
Yep.
So that should make diodes in clear packages. Why aren't they photodiodes?
I should know that, but I think the package is still filtering the light so that it doesn't have an effect, right? Because it's not quartz crystal that allows the UV to get through or anything.
Yeah, I would have said that it probably is a photodiode. It's just it's such a minor effect compared to the geometry of the die is set up to be a rectifier.
We could probably measure that.
We could.
Some clear germanium diodes. I've got a packet of them here somewhere.
1 in 34As.
And it's the same deal. LEDs can be used as if you really need something in a hurry, you can use an LED because like you can generate light with an LED. You can actually measure light with it. They're not particularly optimal for it, but it does work. And I've seen LEDs used as a noise source in a pink noise generating circuit. Right.
Yeah, and so we got responses. Alan just chimed in. Light is just RF with the decimal point moved, which is very valid.
That's right.
And diodes really are. They do have some response to light. The energy of the light would be important. The diode's not a great amplifier. Let's put it that way. So. What we call photodiodes
aren't clear packages do have some are affected by light.
Right. My memory is some of what we called photodiodes are really phototransistors. They really are a gain device. Though they act like a diode, it's really the base emitter junction of a transistor that you're exciting. But that's a 30-year-old memory. Don't quote me on that.
I think there's probably, both.
So if I had real EPROMs instead of the one-time programmable EPROM, here's what I would have had to use. It's like these used EPROM erasers. Yeah, EPROM erasers used to cost some money, right? Now you can get them. This is what mine looks like, and I'll testify that it does work. I don't know if I probably set them to run like 3 different times just to make sure they're erased. So still available from overseas.
Yeah, I didn't like to put my EPROMs in the eraser for extended, too long, because I heard that every time you erase it, you're hardening the actual chip and making it harder to erase the next time.
I hadn't heard that, but I knew there was a limited cycles, like 10,000, something like that they were good for. Yeah,
so I used the minimum sort of time that I worked out with the 2.7 series. I could use 7 minutes or something. The timer would go up to something like 20 minutes, but I could a fresh EPROM would erase after about 7 minutes in the eraser I had, which was just one of those 4-watt fluorescent tubes with mercury vapor and that special quartz crystal that allows the UV to pass out of it. Because regular fluorescent tubes, even blacklight tubes that are for parties and things, that's long wavelength UV.
Right, right.
Which is really almost, it's kind of getting into the visuals.
I've seen some of the shorter wavelength, and you get a pink tinge to it. And when you see a pink tinge on your black light, that'd make me a little nervous, because my dad had brought home a black light from RCA they used to inspect the phosphor on picture tubes.
Oh,
and
okay.
Back in the 70s, they probably weren't as worried about shortwave UV as we are these days, as far as knowing.
Yeah, it's bad news. Yeah, you don't want sunburnt eyes from an ultraviolet lamp. It's bad news.
Yep. So, yeah, I had it, but it was a kick-ass party UV. I mean, it was really intense. So, hey, I have a story about that UV lamp, actually.
Yeah.
We're good for stories, right?
Yes.
So, I used to do lights for a rock group, right, for a local rock group called Primo in Marion, Indiana.
Love it.
And I used to use this black light on stage because it was strong enough, but eventually I broke the bulb, and I ended up with this trough-like metal feature. So what I did was I screwed it to the back of an amplifier, and I filled it with flash powder.
Oh.
And for the last show I did with these guys in Marion, Indiana, the guy was real good at sustain. He pulled a guitar off, had it sustaining, showing it to the audience, laid it down, acting like he's playing, picks it up, acts like he's going to swing, and he hits the strings right as he swung into the amplifier that I had the flash pod strapped to, and I set off the flash pod. Now, I never looked at my own flash pods, right? Because they blind you.
But going to do this.
Yes, we had set this up.
Okay.
I said, when you go to end it, act like you're hitting the amplifier. Here, I'm putting a flash pod on the back. So he did shut his eyes. But it was the last show, the last song of the last show, so I kept my eyes open. And I watched Mitch, the guitar player. First, the guitar disappeared, then his arms, and then Mitch did. The flash was so overpowering to the optic nerve.
I love it.
Yeah. And I had used my ultraviolet thing that I was telling you about. That was the trough. I poured a whole bottle. If you've seen those bottles, usually you do an eighth of a bottle, quarter.
Yeah.
I did a full bottle in this. I mean, it blew it right off the back of the amplifier.
Hey, actually, that's a question. So, they used to use that flash powder. It's called flash powder because it was used for ancient analog cameras, from 150 years ago. Does anyone still make and sell that stuff, or would it be considered contraband in most states because it's pyrotechnics? So, can you get it?
Right. I don't know. I haven't done it for years. I'm actually looking. I did stage crew for Brownsville Station years at once back in the 70s. There's stage crew and road crew. So road crew shows up and stage crews to people, that know their way around the place. And their pyrotechnics were done with LP gas. They had a tube and a...
it's much safer and cleaner.
Yeah.
You can get a nice bright flash with LP gas if you get the...
And a spark plug was trying...
Get it rich, just right. Yeah.
Right.
Okay, so... Pyrotechnics is fun, but it ain't electronics.
Ain't why we're here.
What am I looking at here, Bill? So we've got your 6502 board running with Frank's code. That is beautiful and awesome.
Right.
And then, but to the right of that, you're showing what looks like Quartus, the FPGA design software. So tell us about this.
Okay, so the reason I showed the 6502 was just to show it working. I thought next week I'll show us how I brought it up using a scope, because basically I made my scope into a 2-bit digital analyzer. And I would trigger off the reset pulse and look at the very first cycle of the 6502. That'll tell you whether it's going to work or not. Most of the time, if something doesn't start, it doesn't start, right? And that's what I had. Nothing worked. And I took my scope probe, went around, I put a pull-up resistor on the reset circuit. I'll talk about all that. Didn't help, but that's the kind of things you do, care and feeding of your 6502 until it starts. And you just keep at it till it starts.
Right. We used to put the 6502 and the clock in their sockets first and leave everything else out and just look at the address lines to see that it was counting.
And they weren't doing anything. They were just highs and lows. That's what I'm saying. They were dead, right?
Oh.
And so I'll talk more about how I troubleshot that, but I wanted to show it because I love the vacuum fluorescent display. Frank's code worked first time. It was great because I knew I wasn't troubleshooting code. I knew I was troubleshooting hardware, but as I was working on this. If I'd written the code, I would have had to troubleshoot the code and the hardware at the same time. So it's but the other thing I've got here is my Altera. Let's see if we can see it.
Yeah.
This
looks like this is Quartus.
This is Quartus, and I'm emulating. Go ahead.
Are you able to use the free web edition of Quartus to do?
That's what this is.
Okay,
this is a light version.
So it gives you enough features and support for the chip that you're using that you can do everything you want to do.
That's right. That's right. And
cool.
What I want to do with this, let me show you what this is for. That's the code that I want to put onto this that emulates a 6502. And I've been using the word simulate, emulate. I'm being a bad engineer. I've been using them interchangeably, and that's incorrect. But there's the Cyclone 10 that this is for. And then it's got a little board in between that pins it out into a 6502.
Right, and gives you your level translators to 3.3 volt, right?
It's got level translators on the data bus. And that was part of the problem I'll talk about next week. I left an input floating because I didn't want to tie it to 5 volts and break my part, but the pull-up was gone. So I won't say more about that. So here's the code that I want to that I have dropped into this. I just haven't tested it yet. And what it is...
I'm seeing a schematic here, and you're saying code. And so this just reminds me. So when I was doing FPGA design, predominantly I at least like to start with schematic at the top. It looks like you do as well.
I do.
What's your thought process about why and how you go about
for me
it's an FPGA design?
It's about visualizing the signals first and foremost, the ins and the outs of the part. And honestly, I'm just not as good at Verilog as I am at a schematic. I've been doing schematics since I was a kid, right? So it allows me to define the pins and their polarities. For example, here, I can see real easy that I'm going to key off of let me get a mouse going. That I'm going to use yes. And so RAM select is very easy to visualize as not a 15 in this case. So that's it for me. Is it starts with visualization. And here's the other thing over here. This is a built-in RAM block. So the whole idea of this was a 6502 that can run at 32 megahertz. Well, that's no good. Right? If the external RAM is still at 1 megahertz, why have a processor run fast just to wait on the I/O or on what's out? So inside the chip, I actually have the RAM module. Let me pull it up. That comes with Altera. This is a definable block, and you tell it, "Hey, I actually ran a wizard to generate this because I can't write code like this."
So that's one of their library of parameterized modules.
That's right. That's right.
And the point there is you're not, like, you can look at the code that's in there, but it's mostly going to look like nonsense if you're not intimate with the actual silicon.
Right.
Because the value of using the library from the vendor's IP library, using an IP core from their library, is that it's been optimized for their silicon, right? So I could take a generic, I could instantiate a generic RAM using high-level behavioral language in VHDL or Verilog, and then it would be up to the Altera place and route. Actually, it would be the synthesis tool. The Altera synthesis tool would look at my Verilog code or VHDL. I prefer VHDL. I just know it better, but I'm not good at either of them anymore. I haven't done it in years, but it would look at my VHDL and infer RAM blocks from that, and then I could give it parameters to say to the synthesizer, prefer using block RAM, which is a dedicated silicon RAM chunk in the FPGA that's for use purely as RAM. But you can also have distributed RAM, which is using some of the gates in the chip as RAM, because at the end of the day, the whole thing is just SRAM.
It's RAM
anyway. That's how
with
they
lookup
work.
tables. Yeah.
Yeah. So, and distributed RAM, you don't get much. You can chew up a lot of chip real estate instantiating it that way. But if you need a FIFO or something where you've got one RAM feeding into another, like a shift register, if you want to instantiate a FIFO, distributed RAM is really good for that, because it'll run super, super fast.
Now this board has SD-RAM on it.
Oh, that's cool.
But I'm not using it, but I could have. I have the pin assignments for the, matter of fact, let's see if we can see them.
And they have an SD-RAM controller in there. So this is the other cool thing. These vendor tools usually give you the IP.
I don't see, I think I'd have to use the Altera SD-RAM, but you can, let me make that bigger and you'll be able to see it. You'll see that
they have, surely they have an SD-RAM controller IP core that interfaces the FPGA to an external SD-RAM, and then you can just read and write to it as if it were a static RAM, right?
Yes. Yeah.
Okay.
And I don't know if they have their own or if they just rely on Altera's, is what I'm saying. Because Altera has a built-in SD-RAM controller.
Who's they?
This is Trends did this
for the designers of the board?
Of the board, right. Okay. Trends did this,
so
and this I got this from Arrow.
Okay, so that Cyclone 10, you're saying that has a dedicated SD-RAM controller hard IP in it?
No, I'm not saying that. I'm saying they made the board, they included SD-RAM, and I assume that you can talk to it with the regular Altera SD-RAM IP.
IP core. Yeah, that's exactly
soft core. But soft core, not hardcore.
Oh, okay. Because I know some FPGAs have SD-RAM controllers, but
some do. Yes.
I think most of the time, given the brief life cycle of different SD-RAM families, or what family is the wrong word, generations. A generation of SD-RAM typically doesn't stay in production very long, so they're already trying to gear up for DDR5, for example.
Right.
So DDR3 chips are starting to get hard to get unless you're going for the lifetime supported ones that are used. There's a limited number of them available, which are kind of kept going by Micron and others because they know that they're used in embedded systems.
Right.
They cost a lot for how much memory you get.
Right. So, yeah, I was going to real quick look in the IP library, but that's not going to work real good in this configuration where I'm actually RDPing to a laptop to show you all of this.
Okay.
So that's, otherwise I'd program the part that I've been waving around in my hand. So, but what's next on the hit parade here, is so I have a phase lock loop core in the beginning.
Yeah.
Now, in this case, I'm not listening to the external phi clock coming in, and that's an option I will play with later. This is just a phase lock loop that knocks down the 12 megahertz that's on this board into a 1 megahertz phi and into a 320 megahertz global clock for the whole chip.
Whoa.
So this thing's running at 320 meg.
What?
Yeah, so I'm taking 12 megahertz, multiplying it times 80 and dividing by 3. So it's whatever that is.
That's insane. And this, you've actually...
It passes timing. I haven't run it yet, but that's the... I'm sorry, it might be 240 meg. I may have said 320.
Even that's still like super crazy fast for a 6502.
It's the internal clocking. It takes about 8 to 10 clock cycles per 6502 clock. So that's the G clock for the internal logic.
Right, but then so what's the exact equivalent speed if you could take an actual 6502 and overclock it? What it would be the equivalent to?
A real 6502, they go up to like 4 meg these days, something like that.
Yeah, but what would be the equivalent in your FPGA at the clock you've got it at? What would that be equivalent to in a theoretically overclocked
Well,
6502?
in theoretically, I could do it the 240 meg divided by 8.
Okay, so it's still insanely fast for a
Yes.
6502.
Yeah. And so my plan is to try to run it at 32 meg.
Yeah, so it's essentially it's a 32 megahertz 6502.
Right.
That's cool.
Now, what's not here is the clock stretching circuitry. The idea is when it's fetching RAM internally, it runs 32 meg. But when it needs to do an external access, it has to stop and synchronize itself to the slow 1 megahertz clock. So it'll be going along and it says, oh, external access, wait for the 1 meg clock, do a 1 meg cycle. Now go back to fast, and eventually it'll hit another one and wait for the external
it's
cycle.
Like the 128 switching between 1 and 2 megahertz.
It's clock stretching. Yeah, a little bit. Yeah. Yeah. So that's the clock front end to this. But then here in the middle is a 6502. Let me move him out of the way. This is the 6502 core. I got the reference for this off 6502.org. I posted the link to it, I believe, in our Discord channel. By the way, to get to our Discord channel, you know what? No, I'm not going to do it. I was going to paste the Discord link right in the chat here. But go to Coriolis-effect.com, and the Discord link is right there.
Yeah.
Right. So, so this 6502 core is an offshoot of the actual 6502 netlist. What's that mean? It means that somebody reverse engineered 6502, like the monster 6502 is a variation on that.
Yeah.
Over at 6502.org, they reverse engineered the whole 6502 down to its net list. It's actual connections between gates. There are no latches,
awesome.
Nothing like that. It's just gates and transistors. And interconnects. And that gives me this chip here, which emulates the 6502. We'll drill down in a second. The one thing I wanted to show is it has data in on the left right here. Whoop, let me make it bigger. It has data in on the left,
Yep.
and data out on the right, even though they're tri-state on the chip.
Yep. Because
That's not how it works.
FPGAs can't do that.
Right.
They can't, because the only part of an FPGA, there are some older families that actually can have tri-states internally, but it's super slow. It's the slowest connection
Tri-state
on the
sucks.
inside of the chip. Yeah.
Tri-state sucks. There's no other way to say it. Coming out of tri-state or into tri-state is hard to measure. It's hard to design for.
Right. So FPGA architecture for quite a few generations now has abandoned internal tri-states for having tri-state only on the I/O buffers. So the pins on the outside of the chip can do it. But if you write VHDL or Verilog that implies tri-state inside the chip, you either won't get a working circuit, or you'll get a circuit that can't pass timing because it's on a, and that will only work if you're on something old like a Spartan 2E.
Right.
Some old FPGA architecture where there were still tri-state signaling possibilities in the silicon, which long since
then you
those
need
have been...
pull-ups. You need to define the undefined state of what is it when it's tri-state. You don't want floating nodes internally, things like that.
Yeah, and those things. This is where actually programming the chip and testing it in hardware is really important. And I wrote an article years ago on this because I actually had a customer who was doing an FPGA design and was simulating it in Model Sim, and the simulation showed that everything was working. So his functional verification was, my code is good, this works. I can't understand why it's not working in the actual chip. And we spent a few hours stepping, well, you can't step through Verilog and VHDL, but stepping through the debug you can in a simulator. You just can't do it in actual hardware. And then I thought, stop, no, I've got to look at these 2 lines of code here. And this is looks like it's instantiating a mux.
Right.
And when I looked at the code and I drew the circuit on a blank piece of paper, what if I'm looking at that code, how do I interpret that as actual gates? And I drew the circuit on the piece of paper, and I realized he had an I/O buff with a mux after the tri-state part.
Okay.
And it all came down to synthesis. But the reason this baffled us for hours was because the synthesizer would run and we could download the bit file into the FPGA and it just wouldn't work. Yeah, like it would do all these other things, but that particular part of the design was not working. But
right.
The simulator was showing the correct result. So the simulator will just simulate exactly what you've written in the code. But
got it.
The hardware, after synthesis and place and route, may create something you're not thinking of because the simulator says what you've done is correct and it works in the simulation. So if anyone's getting into programmable logic, that's a big deal. There's a few things like that that are traps for new VHDL and Verilog programmers, and even seasoned people get tripped up by them once in a while. That's one of them. Try not to instantiate a multiplexer or internal logic that is tri-state. Avoid those at all costs. If you are doing things like that, make sure you are very explicit about where the tri-state is, that it's on a pin of the device and not inside. And there's no other logic from the pin. Because the thing was, this was going to a pin, but the user, the guy writing the VHDL, wanted some feedback from that back into the chip.
Right, which you can do.
So we solved it. Yeah, you can do it. We solved it by we just rewrote that line. One line of code was all it took.
Wow.
To feed an iBuff back in from that signal.
Right.
And
right.
that put the IO buff tri-state on the outside of the chip and tapped off the input part of that IO buff. So anyway, long story short, the other one to always avoid is gated clocks. You don't bring a clock in and then put it into an AND gate to enable or disable, which is awfully tempting to do. You want to have a clock enable. There's special resources for that in an FPGA that you should use. Don't use a regular AND gate.
Well, what you're talking about is crossing clock domains, aren't you? If you try to...
Well, partially.
If it's asynchronous.
But even more basic than that, if you have a clock signal going into an input of a gate, you're forcing the clock off of a clock line, which is a global high-speed, low skew line.
Right.
You're forcing it to use LUTs instead.
Right. You've taken it off of that grid, and you're trying to use it as a signal.
Right, and if you have a 200 megahertz clock, it's never going to work if it's in the regular
logic. Right.
Yeah.
So here's the area you were talking about. Let me expand this real quick. Where tri-state does come into it, and that's at the pin itself. Hopefully you can see this.
Yep. So I'm curious how someone gets from a reverse engineered silicon netlist, because you can do whatever you want if you're doing hard silicon.
Right.
With FPGAs, you have to do everything synchronous and be aware
by the
of clocking.
rule. Right. If you want to play by the rules.
Outputs. Yeah.
Right. So here's the 6502 that I start with. Here's the upper level, and this is the wrapper in Verilog. And basically, there's an important line in here called include logic.inc. And the rest of this just references, there's almost nothing here.
It's just the inputs and outputs on the block, really.
That's it, yeah. And then when we
go
to logic...
symbol, which is also a kind of a wrapper on a wrapper,
right,
which is on the logic.
Here's what's in Logic.inc, and this is basically a netlist. I honestly couldn't read this if I had to, without sitting down and creating, back reverse engineering a schematic, basically. So what this is basically a whole bunch of node assignments that are combinations of other nodes, and this is what they call cycle accurate 6502 emulation, based on the netlist.
Are there any register instantiations or other things we could see?
I don't see any. I think the registers are made via netlists. I don't see a single register.
That seems really weird, because to me that would imply that this is actually Verilog, but it's already synthesized.
Yeah,
because it's just muxes and wires in connecting to what? What are the muxes and wires connect to? They must connect to lookup tables and registers in the FPGA fabric.
Right. Yeah, each one of these lines represents a lookup table, most likely.
Well, see, you look O, scroll right to the top. What's at the very top of all this? There's O, I, so I'm assuming those are out and in. And then there's, I see there are some gates instantiated there. So I see an AND symbol. That's an AND gate.
Right.
On line 31 there.
Right. I don't see any periods, for .Ds, .Cs,
and I
CLKs.
see tildes. That's an inversion.
Inversion,
so there's a lot of inverters here, and these are concatenations with the pipe symbol.
Right. And to make a latch here, then they probably have a lookup table whose output feeds back to its input. They're not using register hardware registers. They're using a netlist and lookup tables, and the output links back to the input, and it's basically making a street version of a register. Is the way I look at this.
Can we look at the wrapper again real quick?
Sure.
Yeah, this is so. What it looks
this
like
is
to
slick.
me
That's what
is this whole thing is created by, it's been created programmatically.
Yes. Somebody ran a tool.
Yeah, someone's written a Python script or something that took a silicon level netlist and converted it to raw gate level Verilog.
And in the Discord channel, I have links to the guy that did that.
That's a lot of work, and I'm impressed. And you see the instantiation of the logic that's included. You see it says logic underscores OO dot in NI comma dot O NO. So it's like the internal connections are included with that module logic, and then that's instantiated on line 31. And then the clock is everything's synchronized to the clock by line 33.
Right. So
and the registers are there's registers instantiated on line 27 where your cursor is. That's where the registers. So it's like there's tons of product terms.
Oh, there's the registers. You're right. Okay.
Yeah.
Yeah, I didn't see any down below. Right.
Yeah.
So
that's a lot of work.
Yeah.
I personally rather a 6502 actually written from the ground up from a data sheet in VHDL.
Which
like
they have.
And they're probably not exact cycle accurate, but they'll run.
And they're not meant to be. They're just meant to be. And there may be some cycle accurate on open cores, but I chose the one because I'll be meeting with Bill Mensch. This was originally done last year before the pandemic, 2 years ago. And what I was going to do is go to VCF where Bill Mensch was speaking and show a 32 megahertz. So I was actually going to try and plug it into the Cactus 6502 and have it actually run with internal memory running at, whatever 32 meg or whatever it was at, and actually show that with some timing loops and things.
Nice.
So I wanted it to be based on Mensch's Real 6502. So that's what this is. This draws its heritage all the way back to the NMOS 6502.
That's cool.
So, all right. So one thing I did want to show real quick, just for somebody getting started in Verilog or VHDL or FPGAs, is I wanted to know, am I doing it right? You know, hang on, so here's this little thing, and I had to download or upload into the tool the assignments for all the pins. This is a real compact BGA socket. Where you see the pin assignments N1, M4, P22. I wanted to make sure those were right, and on this board they do assign some LEDs. So I said, you know what, I want to just blink the LED, and I ended up doing it in less than 5 minutes. And actually I didn't write a line of code. I wanted to show how I did that. So basically, let me get my glasses on here. I Googled for an LED blink routine. Yes. I said, I don't want to write even a line of code because I don't want to make a mistake. So I found this line of code. I made it into a Verilog file. I saved it as blink.v. And the first thing I did was I went to project, add and remove files from project, and I made sure that blink.v is now part of the project. It won't know what to do with it till I've said, you know, by the way, I made a file and I want it to be part of this project. And he goes, okay, part of the project. And then I said, okay, here it is. I want to make a symbol out of this. So I did file, create, symbol from current file. And I'm not going to do it. I'm going to hit cancel, but it's saying, hey, something's been modified and whatnot.
Yeah.
It will actually compile this little Verilog thing and make a symbol. And then out at the main sheet, I said, hey, I want to place a symbol. So I clicked on my little NAND gate, went to project, and there's a blink symbol with the clock and the LED, the only two signals on it, and I could instantiate it.
Yep.
So almost in the time it took me to demonstrate that, I made a LED blink.
Super easy.
Yep. And the trickiest part, and it almost always is, hang on, it needs a distinct escape key. You get used to so many CAD things, but right-clicking won't drop the instantiation process. You actually have to hit the escape key. See this assignment of M4, I had to go in to the assignment editor,
Yep.
come down, and it's the last one I entered. There it actually says T13. I don't know why that, what's going on there. But I assigned it to the pin that I wanted in real life to come out. Who's got the M4? Why is it like that?
This is M6. That's what
M6, I mean, yeah. So
let out 0.
Yeah, I'll figure it out offline. I suspect this is wrong.
Here's the thing. Those pin assignment files, every FPGA tool has the ability, because this is a ball ache otherwise, to be able to export and import those. And you can do it from Excel spreadsheet. You can do it from a CSV file. And so that's one of the things you want to be able to do when you're designing the hardware is I've designed a board with my Lattice Mark X02 as the core part on that board. And I just want to give a shout out to one of the Eagle/Fusion 360 electronics users who's a guru, Rachel Peterson. She's an electrical engineer in England, and she's a ULP scripting genius. And I put a question to her just yesterday. Oh, do you have any ULP scripts for synchronizing FPGA pin assignments from your PCB or schematic to the FPGA tools? And she's like, oh yeah, I started working on that, and then a job took over, and I dropped the project a while ago. But yeah, I might look at that again, because my current design's using a Xilinx part, and I came back the next morning while she was at work in the UK, 8 hours ahead of me,
Right.
She just went ahead and did it. Bam. Oh, here's a ULP. Try it out for your lattice part to synchronize the pin, the net names assigned to the pins on schematic
Right.
to
Right.
a CSV file, which the lattice, or actually she made the script so it formats to the specific vendor format. So if it's Xilinx, it'll be XPT or whatever their file format is. And I'm just like mind blown. Like some people just
somebody
can't
made
help
it look so
themselves.
easy.
You give them a little problem and they know how to solve it. They just go do it.
Right.
So
now that's an important point.
I don't know if Rachel's the kind of person who likes to talk on live streams, but she's the kind of person I would want to join us one day for just as a guest. She's amazing.
Now, are you able to use that ULP in your Fusion 360? Then you should be able to, right?
Yes. So that's the whole thing. I can run this ULP and generate the pin file directly from my PCB design, well, from my schematic, basically. There's a few caveats to how I name the device and how there are probably some attributes I need to add to it, parameters I add to it. And this is good because, I used to do FPGA PCB CoDesign back with Altium and Altium completely abandoned the whole FPGA and embedded design thing. They even just sold tasking off the compiler company that was a division of Altium. They just sold it off to some private equity company. And I was really sad when they did that when I was still working there. I didn't agree with it. It wasn't but my opinion didn't matter, obviously.
Okay.
But there were thousands of people doing FPGA and embedded design using the tools, and it just all got nixed, but whatever.
So there's a process. There's a process, though, for allowing pins to be swapped during your design PCB phase.
So that's the whole point. I can set up in Eagle and Fusion 360, and I know Altium can do this, although the synchronization piece got cut out by Altium when they abandoned the FPGA thing. So I disagree with this, but but you can configure the parts in the library to be pin swappable. You can configure pin and gate swapping, and that's super useful even for resistor packs. But the primary function is for microcontrollers and FPGAs. So I can do pin swapping and optimize the rat's nest on the PCB, and then that gets synchronized to schematic, and from there I generate a new pin file, and all my pin assignments in the FPGA tools are updated. Or I can re-import that into my FPGA design. So it saves a ton of time. But the real benefit and reason why you should do it with software is that you're not going to make a stupid mistake. If you have to use an Excel spreadsheet and manually synchronize things and keep them up to date, somewhere along the line you're going to get really frustrated and have something out of sync.
Right. So, right. You could go so far as to have the auto router do auto repin assignments if you were into that. Yeah. And be able to extract that out as a CVS file, if nothing else, and re-import that back into your PGA design tool.
Right.
And keep iterating through that, because the PGA design tool might said close, but now I can't route the chip. Usually you can these days. It depends how much room you leave yourself.
That's right. There are caveats to doing this.
Right.
The value
of
the
bank I/O and
any
stuff.
pin assigned to any signal, you can do that, but it makes place and route more difficult.
Right.
In the FPGA tool, and it can slow the whole thing down. I spoke to some gurus who did like LED video panels are cheap and easy to get from China now, but 10 years ago they were made here in America, and they used FPGAs to be able to do full motion picture, full speed.
Right.
And to be able to clock data through that quickly across a display, a full HD display on a stage or whatever, it takes some pretty high speed capabilities, and FPGAs at the time, like 10 years ago, were the only devices that were capable of this. And so there's a company up in Berkeley or in Berkeley area called RGB Spectrum that making high-end, designing and manufacturing high-end LED walls and video display, multi-screen.
Like at rock concerts, you'd see them and stuff.
Partitioned display.
Yeah.
And also, airports and all sorts of things. And so all their designs used really expensive FPGAs like Vertex series. And the guy there who's an absolute guru and had been working with FPGAs for years, he told me, like, we've discovered just by our own design efforts and trial and error that if you look at the FPGA and the pinout on the data sheet, it's got north, south, east, west. If you tend to control your place and route,
right,
and assign your I/O pins such that you're always going from one side of the die to the other.
Okay.
Typically east to west, but you could go west to east.
Right.
But if you pick a direction and go in that direction with your general data flow, then you meet timing requirements and everything works at very high speed. But if you just randomly assign, or not randomly, but if you assign to...
Let it randomly do it. Yeah, you're tripping over yourself.
If you assign the pins to favor the circuit board design more than anything else, then some things will be asked backwards in the signal direction, and the whole thing slows down, and you may not meet, or probably won't meet, timing requirements. So it's just an interesting, and it makes sense if you think about the way the silicon's structured in these things. They typically are, and they have, the people that design the FPGAs are very smart and know what they're doing, and they put things in columns going left to right, and they have all the multipliers and block rams down the center for a reason, and they put the multiplier accumulates or DSP blocks right next to the block rams for a reason. You got to be able to hook them together, lash them up together intimately so they can operate really fast and do FIR filters and things like that. So
right.
Yeah.
So it's been mentioned, Frank mentioned it, Chris mentioned it, KaiCAD does not have pin swap capability, that somebody needs to write a plugin for it. So I'm a little surprised to hear that. Yeah,
well, it's open source, and there's a lot of contributors to it, but until, like any open source tool, until someone actually needs it themselves and are willing to invest in it, it's probably not going to happen.
Or till somebody buys the tool, like they did Eagle, right?
No one can buy KaiCAD. It's completely GPL.
Completely, yeah.
No one can buy it. It's not owned by anyone.
They can't buy it. They can't buy and make their own version of it. Then the license instead of.
Well, the only thing you can do is employ developers to build from it, and that's what CERN have done, right? But they don't care about pin swapping as much as they care about differential pair routing, say, and push and shove vias. So that's being done, but they haven't done the FPGA.
What's your impression of KaiCAD in general? I'm an Altium user. You're an Autodesk person. How's KaiCAD? Does it have any glaring deficiencies compared to those two packages?
Well, I think the community probably already knows all this, and part of me says not to answer that because I don't want to give them any hints.
Well, I'm trying to kill the last 5 minutes of the show, so feel free to do whatever.
KaiCAD has come an awfully long way. It's clear that it is now the PCB design tool that will survive of all the open source tools that have come and gone. It's the only one that's actually usable professionally. Let's put it that way. It has a few glaring deficiencies, namely the user interface in schematic and the user interface in PCB and the user interface where you design library parts are all kind of different and don't use one common set of paradigms. And that was the strength of a tool like Altium or Eagle, is that you've got one UI that works in every part of every corner of the tool, and it's sensible, and it's well structured, and it has been well thought out. And you get that with professional commercial software because you have whole teams of people employed to do it. It's their job, and they're typically trained professionals rather than hacks. So KaiCAD will probably always be a fairly clunky experience and have weird UI things because it doesn't have a dedicated full-time paid experienced designer, let's say. Yeah, library development in KaiCAD's a pain. I'd hate to have to make a 144 pin, device like the Mark X02 that I'm using on my design, let alone a 1152 pin BGA FPGA device.
Do they have?
Like, you'd have to be a skilled Python programmer to be able to use KaiCAD and be productive and efficient with it, because you'd be constantly writing little additional Python scripts to augment what you're doing.
What's the format? Is it IBIS is the format where you can, and Eagle, I used to run a ULP that would import, and
Yes.
in Altium you can do that as well.
Yeah, most commercial tools will have some way of getting parts designed quickly.
Right.
And if you really get stuck, you use SnapEDA, and I guess they have a business too because of the large number of KaiCAD users out there who don't want to make their own parts because it's such a pain. You're likely to set up an account with SnapEDA and download them every now and then.
Right.
So,
yeah, I'm trying to think of what the name of the package was that integrates with Proteus. They kind of do the same thing as the ECAD or the company you just mentioned, plugin.
well, it will be Ultra Librarian probably.
That's it. Thank you.
Ultra Librarian have a plugin for every ECAD tool that's popular.
Right. And
so
one of the things I used Ultra Librarian for was the IBIS import.
Yeah. Yep. So it's, for those who don't know, IBIS is IO buffer, Intel buffer. No, what does it stand for? Have to go to the website again. We've said this before. IO buffer interface standard or something like that. It's an open file format that describes the switching characteristics and the parasitic nature of every pin on a chip. So IBIS is used for providing the models for a device for signal integrity analysis. So it basically, you can download an IBIS file from Altera for the chip that you're using there, Bill.
Right.
Download the IBIS file, and it has all of the different simulation models for the IO buffers and all their different programmable options on the chip. So if you program the Altera, one of the IO pins, if you program it with a fast slew rate and 8 milliamp drive strength, and it's LV CMOS 33, then it picks the right IBIS model that simulates the IO drive and receive characteristics, the inductance, capacitance, resistance of the pin, and also the clamping diodes that protect the device.
Right.
All of that circuitry is included in the IBIS standard model that you select for that pin, so that when you run signal integrity analysis in an SI simulator, it's using the pin as it's going to be used when you program it.
Right.
So that's what IBIS files are for. But what they do is they describe every pin and what the pin numbers are as well. So you can actually take an IBIS file and turn it into a schematic symbol, and it even can name it'll even name the package variants. So if you know what those package variants are for an Altera device, then you can actually also, in theory, use an IPC footprint wizard that creates the footprint for it as well. So IBIS contains a lot of useful information beyond just the simulation. Yeah.
Right, right. Yeah, I looked it up. It's input output buffer information specification.
There it is. There it is. I knew
Yep.
I was close.
Yep, yep. So,
Yeah.
well, that brings us to the top of the hour here. So
Yeah.
it's there. We do have some discussion going on about KaiCAD. And it looks like good information about whether dedicated resources are needed to produce something like KaiCAD, or what benefits from what.
Yeah.
So,
I actually agree, Dark Nace, with that statement that if more people are using the software, then there's naturally going to be more contributors to it. I agree with that. But think about this. How many software engineers exist in this world? And how many people who use some flavor of Linux exist in this world? There are literally billions. Literally billions. How many people in this world design printed circuit boards in a given year? I've looked at the research.
100,000.
Naturally, because I work for an EDA company and I need to know how many people can we sell
right.
to. What's
How big's the
total
market?
addressable market?
Right.
It's about 100,000.
That's what I guessed. Yeah.
Maybe 200,000 if you include. Maybe if you really stretch 500,000 if you include all the hobbyists and makers who we're not going to sell to anyway. And those are the people, frankly, using KaiCAD or they're using the free version of Eagle. So the total number of people available from that pool of people, and then narrow that down to, of those, how many can actually write software, and of those, how many are actually willing to spend their time writing software. It's a very teeny tiny pool of people. And that's why I say it takes a commercial entity that has an interest in using that software to really push it forward. And that's why CERN employed 2 or 3 people to just work on KaiCAD to build out the things. And even, I don't know if that's what they do all the time. I just know that they've employed some people, and part of what they do is contribute to KaiCAD. So, if you look at the actual numbers, it's pretty limited, but it's true. Like, that's the whole point of open source. The whole open source
idea,
modus operandi or idea, is that just because it's free software and it's open doesn't mean it's not for commercial use. And as we've seen with Linux, it's exploded and it is used in billions of places, because the whole idea was to make something that could be used for commercial purposes. And so naturally all these companies sprung up, and resources and people who could train, and consultants, and it created a whole new market when it's an operating system that could be used on anything from a small embedded device all the way up to Amazon's data centers and Docker and Kubernetes clusters and crazy awesome stuff that's come out of it. I just don't think EDA is a big enough market to get that same kind of momentum, but I could be wrong. It would be good for the users if I'm wrong, but meanwhile,
good point.
I work in EDA, and I think there's a good reason to pay for good software that is dedicated to that purpose, and people's sole job is to develop it and make sure it's a good UX and productive.
Right.
So, yeah.
Right. And I go along with that a little bit. I pay out of my pocket for Altium because I want something that in theory works, and if it doesn't, in theory I can call them and say why not, and or what am I doing wrong, or make a feature request out of it.
That's true too, and in the operating system world, that's where the consulting and the professional services comes in. So maybe there's room for someone like Chris Gamble, who knows KaiCAD like the back of his hand. He could, as part of his consulting services, he could offer support and training for that product. Right. But instead, he's just put all his training on YouTube so anyone can watch it for free. So
very good.
He's not going to make money out of that, probably, even though he could have.
I'm not touching that one. So, All right, my friend. Well, it's now 5 minutes after the hour, and we had a good discussion. Got into Quartus and ibis, however you say it. One of those is a bird, right? And I'm probably saying the bird's name and stuff. Yeah.
Well, I think that's the logo of the. If you go to ibis.org, they have a bird logo, which is an ibis bird.
Okay, that makes sense.
I see them around here in Southern California. They land in my property every now and then. They're really nice looking birds.
There's probably an O'Reilly book that features an ibis on the cover of it, I'm assuming. Yes.
They've had every normal and every obscure animal by now.
Animal ever, yes. Yeah, I had a whole zoo on my bookshelf back when I owned an ISP back in the late 90s and then the 2000s. We lived and died by the O'Reilly books. It's basically told us about the rules that were developing around us, and without O'Reilly, I don't know I could have kept the ISP running every single day like we did.
Yeah.
So hats off to the zoo.
Quite a few. I've got a few still on my shelf too. I've got there's a few over there. I see a C sharp.
I've got thousands of dollars worth of Cisco books. I'll give away to somebody. You just have to come get them. So,
cool,
all right.
Great to see you.
Good talking with you. We will see you next week.
Yeah.
Yep. We'll figure out something to talk about and take it from there.